Hi and welcome. Today we will dive into the fascinating world of organoids, as self-organizing 3D mini organs that are revolutionizing the biomedical research. So, what is an organoid? An organoid is a three-dimensional tissue structure created in the lab from stem cells. What makes them unique is the three key features what they have. First, their incredible ability to self-organize, much like that happens during real organ development. Second, they are multicellular, meaning they contain different types of cells we can find in the original tissue. And third, they replicate key function of that organ. It's just amazing. Organoids can be generated from two different main sources. On one hand, we have the pluripotent stem cells, which have the potential to become any tissue type in all the body. And on the other hand, we have the adult stem cells, which are extracted directly from a specific tissue, for example, a biopsy, and are cultured to form an organoid of that same tissue. For over a century, research lay on 2D cell cultures, where cells grow in a flat layer. These models often fail to replicate true tissue physiology. A flat structure limits the critical cell-to-cell and cell-to-matrix interactions that drive a tissue dysfunction and disease. Organoids solve this by bridging the gap between simple cell cultures and complex animal models. By growing in three dimensions, they create a superior microenvironment that better mimics the real tissue, architecture, and cellular interactions.
In recent years, 4D fabrication has emerged as a powerful tool in tissue engineering. Unlike traditional scaffolds, 4D systems can change their shape and properties over time, mimicking the dynamic behavior of living tissues. In 4D tissue engineering, the focus is on developing cell-based structures that can adapt and respond to different signals in imitating biological processes. This involves combining living cells and with smart shape changed materials and advanced fabrication methods. There are three main strategies in 4D tissues. First is 4DA, and the scaffold is made without cells. It activates first to change its shape, and only there are cells added. This protects the cells from stress during the transformation. Second is 4DB. The scaffold is made and cells are added before the shape changes. Then the transformation happens and the cells um, experience the dynamic change in their environment, which can help their growth. In 4DC is the most advanced method. The structure is created already containing living cells. These cells, filled construct, can quickly respond to signals and change shape, making them very similar to real tissues. Shape-changer materials are special smart components that can change their shape when exposed to signals like heat, light, and moisture. One important group are shape memory polymers. These are smart polymers that can be programmed to return to a permanent shape after being deformed. Another group are shape memory hydrogels. These are hydrogels that change shape by swelling or shrinking, um, and they are especially useful in biomedical applications.
4D fabrication has emerged across four major tissue engineering domains. Bone and cartilage applications use shape memory scaffolds that adapt to irregular defects and provide optimal mechanical support. Cardiovascular systems include self-expanding stents and cardiac patches that conform to heart geometry. Neural applications focus on guidance conduits and brain tissue models that respond to physiological cues. Muscle and respiratory tissues benefit from dynamic scaffolds that provide mechanical stimulation during tissue development.
The clinical translation of 4D tissue engineering follows the three critical stages. During implementation, compressed constructs enable minimally invasive procedures, reducing patient traumas and surgical complexity. The activation phase occurs in vivo, where scaffolds respond to the body temperature, pH, or other physiological triggers to achieve optimal shape and function. Finally, the integration phase provides long-term benefits through dynamic remodeling that matches natural tissues healing process. This technology represents a paradigm shift through truly adaptive medicine in plants.
The current challenges of this project are the limited cell integration during fabrications. The most systems are one way only, lacking reversible shape change. Also, programming SMPs is complex and not easily scalable. The biocompatibility and biodegradability of smart materials still needs optimization. Also, few in vivo studies on clear immune or tissue response. And the final problem is a technical trade-off, resolution versus cell viability versus material compatibility. For future perspective, we have the development of biodegradable multi-responsive materials, the creation of reversible shape memory system for dynamic implants, also expand application to drug delivery, cancer therapy, and neural and cardiac models, to increase in vivo validation for safety and long-term function, and also combine 4D fabrication with AI, bioprinting, and microfluidics to personalize therapies.